start. Okay, the last pause is the hardest one. So in this case, we're going to have unbelievably exciting vector fields. Let's write down the definition. A vector field f is a function that associates with, to each point xy, a vector f, capital F, of xy. For each point, we will have a vector field. That's the idea. For each point, we're going to have a vector f, a vector field f. A vector field on R2 is a vector function. So, f, this is, I guess, one of the most important formulas. You see it quite a lot. Capital F of x and y equals pi plus qj. Pi plus qj. One of those formulas you can draw. You can write this formula in Japan. If you go with exchange students to Japan, and they should recognize it if they took Calculus 3 class, even if it's not called Calculus 3 class. So in Ukraine, we had Math Analysis 1, 2, 3. So that's when we learned it. But this is a very famous formula. F equals pi plus qj. Assigns to each point xy from D the vector f. So from 2D to 3D and so on. It's easy to explain through examples, but can you guess? I kind of accidentally already spoiled examples of vector fields. What do you think? For now, it's not very clear what the heck we're doing, but we have collection of vectors for each point. So this point has a vector. We just learned it months ago. And this point has a vector. And this point has a vector. And this point has a vector. What does this remind you? What? Gradients in the nature. What do you think is that can be? What? Slope field in the nature. And biology, medicine, physics, yes. Magnetic fields, right? Like you drop a stone. What? You drop a metal ball. Where it's gonna go depends on the magnetic field. There are lots of examples. Do you have any relatives that are right now in tornado zones? So scary. Many of my online students emailing me that they are hiding in the bunkers and they have livestock to hide and everything. Super scary. So right now there's lots of tornadoes. Like this is exactly vector fields, just the one that want to kill everyone. But they are still vector fields, and we're going to learn about how strong they are, why do they spin, that's called a curvature, and so on. Usually they're color-coded to see. See, all the little arrows are the same. That means the vectors are unit. We want to see where the thing is going. Then the strength is usually color-coded. So something is stronger here and very strong here. That is an example of a vector field. Wind map. You don't have to draw it, just example. Ocean currents. Have anyone thought about that? If you drop a bottle, plastic bottle, at some point, probably we're going to circle around the world, which we already had like, studies about that. And I do recommend you to read a book called Moby Duck. It's called Moby. Yeah, you know, right? I went to Seattle and they promoted this book. At some point, those plastic cute bass ducks fell off the container. You know, everyone forgot about them. But then they started finding them in the places of Europe. That was in America, I think, or Japan. They found them in places in Europe where not supposed to be. So that changed the map of oceanology because oceanologists did not know the subcurrents of the main currents they knew before. So they actually started asking normal, typical people if they see a duck with specific number to report it. And that's how they could connect the ducks from here end up to be here, and they were not supposed. So it actually changed the science of oceanology. And now they're studying it using drones, and like they drop something and see where it's gonna go. Same as they do with birds to see migrations. And then I also have some really cool stuff here. You know, classical idea where you're gonna go. Vector fields, you see? All the vectors are unit. Pretty cool colored graphs of vector fields. People do studies on bees and flies, especially bees. They do want to see where bees go, how do they migrate. Do you know we have migrations of bees in Arizona? So one day you can wake up and see bees hive in your yard. They're migrating. They will stay for 3-4 days, rest, and move on. So all of those are also vector fields if you want to see where it's all going. The most classical one is this one. This graph actually will be in your homework. Vector fields have different properties in different locations. Some of them do circles at the edges. Some of them pull you to the middle. Some of them pull out from the middle. So it kind of depends on your starting point. And this, check it out, this F. We're going to be doing integration via vector field. Look at this. How to find the path from the first point to another point. Well, it is a 3D path. It's not just a line in 2D. So when we go to 3D and we're adding vector field, it creates some kind of 3D picture. This is actually the best application because I will make a point that vector fields is kind of collecting all the possible points on the way of your walk. So you are scooting, you're biking to class today, and it's windy. Sometimes wind is towards your face, to the side, away. So we want to know that. We want to know where it's going to go and which kind of strengths it has. Wow, my voice lasted for 5 minutes. That's crazy. We can illustrate a vector field by plotting each point of a vector with its tail. So tail is at the point x, y. For example, sketch f of x and y equals x, y. You will be struggling with this homework. It has like only 7 problems, but they all graphs. And I know you don't like it. It comes some visualization though. It's pretty cool. So before we had the point x, y. Then we had a vector. But now we have lots of vectors depending on the input. So it becomes a vector field. So let me change the color. This pair is a point. But this is a vector. Vector with a tail at the point. So tail goes away. The tail is at the point. Let's see what is f of 1, 1. When I want to find what is happening at the point 1, 1. So you're standing at 1, 1. Will this ball in magnetic field will be pulling away to the right, to the left, north, east, blah, blah, blah. I don't know. That's where the vector field comes in. It tells you where the wind is blowing, where the magnetic field is dragging you. At 1, 1, that is x, that is y. You plug in, well, x gives you x, y gives you y, so it matches. It's like a very dumb vector field. Okay, so now you know how to draw a vector 1, 1, like that, or whatever. So, and the strengths here doesn't matter, that comes later. F at 3, 1, guess what, will be 3, 1, and so on. So it seems like it's matching the x and y because that's how it was defined. It's an example. X matches x, y matches y. Looks like that. Let's describe together. Make a sketch. It's kind of like a explosion, I guess. I like explosion. So everything's pulled out from the center. Why? If I want to see what's happening at 0, 0, then nothing is pulling me at 0, 0. Because, let me remind you, F gives you 0, 0 vector. Yes?
It sounded like from your description that the tail of the vector is where the point is, but it seems like from like these pictures, it seems like the point is kind of the origin of the vector.
Very good question. I'll show you this right now. Also, they're not the same, as you can see. So, this happens with the, like this, yes. Let me show you the example. You take this first point, it is located at 1, 1. But then the vector is given as 1, 1. And then the vector, we know how to draw it. Vector has a head at, vector is drawing like this. X is 1 unit. So I will go here, find 1. Y is up, 1 unit. I'll go up, here it is. So 1 and 1. starting point 1, 1, and then vector matches it just by definition in this specific example. And you know how to draw it. Whatever to the right, whatever up.
Yeah, so the vector goes like 1, 1 from the point.
Mm-hmm.
Yeah, so you start from the...
Yeah. Let me explain this example. Check it out. How about this one? This looks like, 1, 5? I don't know. I just made that, but it looks like 1, 5. Let's see how to draw 1, 5. It starts from the point 1, 5, but because x is x and y is y, it will have 1 point, 1 unit away from this point, so not from the beginning anymore. So this is 1 length to the right. I'll make a triangle. 1 to the right and 5 up. Yeah. So now this point, the head, is a different point. Make sense? Did that answer your question?
Yeah.
That was a really good question. Do you understand? The beginning is the point, but the vector is a different thing. And we learn how to draw vectors. Vector tells me how much to stretch to the right and how much to stretch up. And in this case, it's 1 to the right, 5 up. Then you connect the point using this triangle, and you have a vector. So for this function, at the point 100, 100, that's a point, I will get a huge vector, 100, 100. Not only is it going to be very far, but it's going to be very strong. So it's pretty cool visualization here. When we're close to the center, the strength is very tiny, 0.5, 0.5, negative 0.5, 0.5, negative 0.5, 0.5, and so on. It's tiny. And the farther I'm going away from the center, the stronger it gets. So it's pulling you apart. Pretty cool. So that's a cool example of a vector field. The strength is pretty small at the center, and the farther you go away, the stronger it gets. Do we know examples of this kind of vector fields? When it's not very strong at the center, but gets stronger the more you go away. And it's pulling you away also. Think about the example, and let me know at the end of the class if you figure it out. Many applications. Force fields, that actually can be called a force field. It's forcing you to go away. Velocity fields, gravitational fields, electrostatic fields, emotional attraction. Yeah, sure, I guess. Like, the farther you're away, the more you're attracted. I don't know. Or, whatever. Yes. Let's practice more so you have a good idea to do what to do with your homework. Your homework is full of graphs, but luckily I did solve some of them in my videos. F of x, y, this time it is minus y and x. That is so confusing. Like you will see why in a second. This is so confusing. Your brain will have to get used to that. Every time you have a point x, that will give you minus y. How cool is that? So let's try. F at 1, 0, for example. So it's 0, 0, it's not interesting. That's 0, 0. But at 1, 0, you have to take a pencil or note, maybe if you're good at this, and write down this is my x and this is my y, and I'm fixing a point, 1, 0, on the graph. Then it gives me a vector. The vector is minus y, let's remember, minus y, comma x, right? 0 goes to the x minus 0, and x goes to the y, 1. Isn't cool? So you can do anything like that. So actually it is a vector 0, 1, and we know how to draw a vector 0, 1. No change to x-axis and up. So it's perpendicular to the x-axis. Tell me, what do you think is going to happen with, let's put it here, 0, 1. How does 0, 1 looks like? Negative 1, change the y sign. Negative 1 and 0. Exactly. Good job. And so on. So you can draw these, and then you can actually sketch the graph. So let's do it together. All right, let's have 4 of them, I guess. I want to see the pattern. What is happening with the pattern? So if I did 1, 0, 0, 1, what else should I do? I want to go around. Yeah, exactly. Maybe it's a whirlpool, so I want to see that. What is happening with minus 1, 0? 0, comma 1. Agree, disagree? Waking up? Okay. Good job. That's how I like to check if you're sleeping. f at 0 minus 1. I like that the first one is easy. 0 goes to 0, and minus 1 becomes 1. Good job, people. So, and I would say like at 0, 0 is the easy one. It gives you 0, 0. Okay, so we start at 0, 0. Let's draw this. Have enough space, though. It will take some space. X and Y. For now, we have vector fields in 2D, but we're getting to 3D right after that. For now, we just like see ocean maps. They are in 2D color-coded, so coloring tell us how strong they are. But for now, everything is in 2D. See, so all this, in this case, it's actually warm and cold temperatures are color-coded. But then we're going to go to 3D, which is magnetic fields, and everything is in 3D. Everything cool is in 3D and high dimensions. At 0, 0, it's not pulling me anyway, so I'm at 0, 0. But then at 1, 0, so now concentrate how to draw that. I'm putting a point on the graph, 1, 0. 1 to the right, 0. This is the point 1, 0. 1, 0. From this point, I've been pulled away with the vector 0, 1. How to draw vector 0, 1. From that point, no change in x, but sticking out up. Like so. Do you get it? And we kind of can calculate the size. It is 1. Now at 0, 1, 0, 1, it is here. In general, I try to find all of these points, minus 1, 0, and then 0, minus 1, to see what's happening in the circle. So at 0, 1, I've been pulled with a strength minus 1 on x-axis. That's to the left. And I've not been pulled up or down. So it's parallel. Like so. 0, 1. Minus 1 and 0 is pulling me, no pulling over the x-axis, but then pulling me down, right? Because of the minus sign. Like so. And then the last one pulling me to the right, but no up. Do you see the pattern? If I will keep looking for more points, for more points and then more vectors from there, it creates a vector field, 0, minus 1. That is where will link me around, so circling me around, at least here, right? See how cool it is? Is this a swastika? I hope no, so don't think about that. Just ignore what I just said, but I just noticed like a second ago. Yes?
So why, for like example, the 1, 0 vector or point, you have like going up 1 in the x direction when x,
Let's see.
Up 1 in the y direction when x is I guess I kind of
Oh, yeah, this is a very good question. See, like this is what we need to make it clear. This is a point where to start. And this is how to go, kind of the idea. So we're fixing start, where to start. So I'm starting at 1, 0. That's the point you asked, right? And now I'm forgetting about 1, 0 from this point. Like that's it. I just need to fix it. After this, I don't use it anymore. I only use right-hand side. Right-hand side tells me draw a vector 0, 1. That's what we're learning.
So you don't care about
January, exactly. That is a fixing location. But after this, you draw a vector 0 on the x-axis and 1 on the y. So that's up. Make sense? We're talking about this one. Very interesting. If I find more points, do you think it will be more like that or not? What if, like some kind of random point over here? I don't know, let's just code it with like a different color. 3, 5. What is happening with 3, 5? Is it also perpendicular? 3, 5. What vector is going to give me? -5 and 3. Let's draw it. So I'm fixing the point 3, 5 and forgetting about this. -5, that means to the left, and I'm drawing a triangle, remember about that. -5 to the left, that's quite a lot. Oh, it's actually to this here. Because, no, it's a bit earlier, here. This is 3. Let me think, -5, so it goes more, like here. Now we're going 5, we're going 3 up. You see, I almost messed up. We're going 3 up, not 5 up. So left, up. 3 up. And now I'm drawing this vector. Here it is. Oh, so the other vector is actually not perpendicular. But it keeps circling around. It looks like that if we keep drawing. And so on. So it is a very, you can see a nice pattern. It goes counterclockwise. That's the idea here. Does that make sense? My sketch like it's okay. I think could be better. -5 to the left. 3 up. Oh, probably it needs to go higher a bit. Up. Like this, I guess. Yeah. So for this case, it's pretty cool that F, the whole vector field, is perpendicular to XY vectors. So anytime we choose something, we'll have perpendicular relationship. We can actually check that because if you multiply F, which is -y times x comma y, that's like a classical one, right? X comma y. Then you will have a dot product. The first term is defined as -y and x. The second term is x comma y. If you multiply it using the dot product properties, you will have -yx plus yx gives you 0. If dot product gives you 0, those two vectors are perpendicular. That is the idea. So we can draw. It's fine. We can draw a picture, I guess. Every time you choose a vector x comma y, this vector field will bounce you perpendicularly f of x comma y, like so. It's perpendicular relationship. What do you think about that? A little bit confusing, but it's always at the very beginning of a new chapter. It's always weird. Yes?
How do you know when to do the negative yx versus the x negative y? Or like when you can flip it?
Oh, this was defined. You mean this? That,
so, yeah, because...
that was given. This is an example and it's just given.
Oh, so each problem will be given?
Yeah.
What it's equal to?
Yeah.
Okay.
Yeah. It's kind of like a formula or quadratic equation. We give you a quadratic function and ask you draw the picture. So we're learning how to draw vector fields.
So sometimes it say like f of x, y is equal to y comma negative x?
Yes, it will be quadratic, x squared plus 5. It will be sine x plus cosine x, and that will be hard. So trigonometric actually will create some waves. It's in your homework. You'll see, it's very beautiful. Speaking of which, the question was, is it always x and y minus x and minus? No, it can be worse. So this is another example. Example 3, answering your question. That one is a very beautiful relationship. Minus x, I like this notation more, but you can always do I and j notation, but that's the same thing if you remember. Minus x all over square root of x squared minus y squared, comma, minus y, minus, all over square root of x squared plus y squared. Draw that. This is when people with STEM, after they pass lots of classes, have to have some intuition of what is going on. There's lots of cool jokes. There's lots of formulas written on the board, and two mathematicians keep writing formulas. And then when one turns away, another one just like erases a negative sign, or like adds a negative sign here. And another professor or scientist goes back and like, very funny, and immediately finds the mistake. Some things are obvious for us when we do it a lot. So, for example, e to the x usually has negative because things should be shrinking, not exploding in applications, and so on. In this case, there is also a very interesting thing which you notice when you have lots of practice, I guess. Did anyone notice what happens if I will try to find the size? Let's do solution. Size But that's not professional to say, right? The magnitude. The magnitude of this vector f. F, x, comma, y equals. Did anyone notice? Pretty cool idea here. Square each side, add together, take a square root. Let me do it together with you. Have enough space. It's pretty big. A huge, gigantic, I always say gigantic because it sounds funny. A gigantic square root. Square each side and add together. Then it's going to be x squared over x squared plus y squared. And y squared over x squared plus y squared. What do you think the answer is? Now denominators are the same. So it's going to be x squared plus y squared over x squared plus y squared. It will give you 1. Oh, so all those vectors have size 1. That's pretty cool. F, x, y, they have lengths 1. That's pretty cool. And now you try to figure out some kind of relationship, like where do they go? Where do they point? Let's compare, just like last time, we multiplied by the classical vector called x, comma, y to see the relationship, and we found it was perpendicular relationship. Here, let's multiply and see the relationship as well. So, that was A. Let's do 1 or A. A, let's see the size. B, so the size is always the same. It doesn't increase or decrease. That's an interesting thing to find out. All the vectors are the same. Unlike before, something was like bigger when I was away from the center. If I'm gonna rewrite f x comma y as, so we have, I will not multiply by x, y, I will factor it out. I would say that is even better. So x and y are here. Actually, both are fine. Let me write down and you tell me what do you think about that. Minus 1 all over x squared plus y squared times x and y. That is a dot product. Is that the same thing? So if I multiply, it's scalar product, which looks like dot product. Yeah, I should say that. It's a scalar product. This is some kind of number, which tells me where to point. This is the pointer. So when I multiply, it's the same thing that we had before. We just rewrite the given vector. This is not very obvious, but we kind of did notice that they have x and y. Wanted to factor it out. If there's a repetitive part, here it is. Here's my repetitive part. Why not to factor out the repetitive part, which is 1 over, with negative sign, a square root. So this kind of relationship tells me that it points the opposite direction from the vector x, y. How do I know? It points the opposite direction, regardless of the size. Because of the negative sign. This negative sign immediately tells me, oh, so when I choose the vector x, comma, y, let's do that again. Here's my vector x, comma, y, just like in the previous example. But the previous example, my vector field will bounce it perpendicular. In this case, it will be the opposite direction, f, x, comma, y. This helps us to start building it. I'm not claiming it's easy. Your job is not to be perfectionist here. Your job is to have intuition. That is better than to be perfectionist. Sometimes it's not a good idea to find all of them. It's a good idea to try to visualize what is happening. So every time I'm choosing some vector, the vector field will do the opposite sign. And they all have the same size. So it seems like that stupid square root at the bottom was just to make the vector unit. Seems like they were getting rid of the size of the vector to make them all have the same size, 1. So it's unit. Collection of unit vectors. Unit vectors. So here they are. Normal vectors will be like this: 1, 1, 2, 3, 2, 2, 3, 3. But these vectors changing the sign, so they point the opposite direction. So everything points to 0, 0. At 0, 0, it is 0, 0. How cool is that? So it's a cool idea, kind of like a black hole idea, that everything goes into the center. Again, it's confusing and kind of a little bit annoying, but that's how this whole chapter starts. It's have very cool ideas, so they're a little bit confusing. Gradient fields, that is not going to be new stuff. The gradient field is still a gradient. Just we're kind of going from the gradient vector to gradient field. Capital F, and guess what? It's just collection of derivatives. F with respect to x and y with respect, and f with respect to y. In these cases, a function f, the small f, is also called a scalar function. To differentiate it from the, we want to, it's not bad notation, to differentiate not in terms of derivative, but in terms of to be different, to distinguish, right? What's the good word? Distinguish. So not differentiate like in derivative sense. That's why I don't like when they mixing up the terminology. How it will distinguish big F and small f. So the small f is called a scalar function, just to make it different. But the gradient is not a new stuff. That's going to be easy. That at least that is not new. Vector fields. Here's a very good page about vector fields. I do like using Paul's notes for quizzes and sometimes exams. Their explanation is amazing. Paul's notes are one of the best ones. Khan Academy is good for practice, but Paul's notes are very good for step-by-step explanations and stuff like that. So as you can see, finding gradient fields is a pretty straightforward idea, the same way as before. You just find derivatives. But the cool idea that we're going to learn in soon what is a conservative f. F is called conservative if f can be said to be equal to the gradient f, del f. You remember it's called del? For some f, the small f called scalar function f, we will learn how to find it on Thursday. It's going to be the whole fun process, which we usually put on the exam. So we're going to explain it a bit later. But the cool idea is, what does it mean to be conservative? Just by staring at these two. Can you guess? The left one, the one on the left, is not, the one on the left is conservative vector field. The one on the right is not conservative vector field. What do you think is the difference? What do you think it means to be conservative? Yes. Conservative. So like if you are standing here and those are winds, wind example, or magnetic fields, you're being pulled away here, but with the same size of vectors, the same strength, you pull away here. But also it pulls you back to the middle, but also it pulls you to the left and to the right with the same strengths, down and up to the same strengths. That means the total amount of energy, so we're going to learn about conservative energy fields and so on. The total amount of energy is the same. That's pretty cool. So if I'm pushing you to the right, but someone pushing you to the left with the same strength, that is called a conservative field. And not conservative is everything else, when it's keep accumulating and so on, or decaying. So there's a kind of classical example. Just quickly draw the idea. Here is whatever is pulling down is pulling up. Whatever is pulling to the right, pulling to the left with the same strength. In and out as well. Versus swirling, circling around. That is the idea here. Example for the gradient field. That's a very easy. Seriously though, I'm not like making this up. Let's find quickly. Example, find quickly the gradient field for the x squared y minus y cubed. Write it down. I don't want to scroll down because there's the answer there. Do you know how to find it? Yes. That's not very new material. The first component of the vector will be derivative of this function with respect to x. What is derivative of f with respect to x? 2xy. Do you all agree? Hopefully, you took exam 2, right? And the second component, derivative with respect to y, which is x squared minus 3y squared. That's exactly what the answer is. So at least that is not very new. Derivative with respect to x, derivative with respect to y. Gradient fields. That's good news. We'll have lots of new formulas in this week, but at least that is the same. We're just expanding it into bigger picture. Do you have questions, concerns about that? Can you hear me at the back? Where's my sound up person? Yeah, good job, thank you. So, I gave you some links. Check Amazing Vector Fields, read it, and then you search for the word and neat one. And then you go here. It's really cool. Did I show you all the animations? Let me check. Yeah, I did. Well, right now we actually saw something like that. Pulling in, if you are on the diagonals, from the first quadrant, it pulls in. From the third quadrant, it pulls in, if you're on a diagonal. Second quadrant, diagonal pulls out, and the fourth pulls out. But if you end up to be closer to the middles, it starts circling you around. How cool is that? So if you think about you dropping something and this is the water flows. Now you will see where your stone, or like stones, they do not float. Little thing that flows, a piece of paper. Where it's gonna go? Somewhere. Out, in, or in the circles. So that's the idea. So if you go to the link I gave you, which is pretty cool, and then you search for the neat one. Here it is. This is when you can find lots of cool stuff. Yes. Let me make it dark. Look at this. Not only, this is a cool program because it can zoom in really well. That's very impressive. Someone coded this. Those examples of vector fields. If you zoom out, you see a big picture. So apparently this thing has a center. While if you zoom in at the edges, you don't see the center. You just see the edges, and that's it. How cool is that? I can change what color is doing. If I want to know the speed, I just chose velocity. Hide. Then this gives me the speed. Whatever is faster is in light green, but slower in blue. And I see that. That makes sense. Look at that. How cool is that? Then I want to be the same color. Well, that's boring. Or I want to see the angles. Then it color codes the angles. Whatever is on the here in red goes to the left, even though it goes a little bit up and down at the magnetic field. So if you see it as a magnetic field, whatever is up is blue, going to the right. In the middle, it's confused. See? Some of it, so when they match, when they kind of collapse to each other, blue and red, some of it drags you to the right, some of it drags you to the left. What does it create? A circling effect. Albert, this is cool. Pay attention. You'll be doing it for your job, I'm pretty sure. Computer science is probably going to be doing that. This is very cool stuff. Even for creating computer games, it's used. So, just totally called you out. That was very funny. I found it funny. So again, this is rain kind of ideas. Where does it go? I don't like uniform. I want to see the speed. Not really different. They all have the same speed, as you can see, more or less. But now I want to see the angle. Oh, then it gets interesting. The angles are different. Some rain goes directly down. Some is moving to the right and then down. How cool is that? More. Oh, that's not the one I need. And there's so many more cool things if you go to this page. I feel like I broke something. Get ready. This is a pretty cool one. that looks pretty cool. Look at that. So everything goes to the left, but then at some point it kind of becomes very not active on the right. And it have different direction to the right and to the left. I want to check how speeds are different. And this is my speeds. Apparently speeds are more or less the same. So that's also pretty cool. Oh God, it keeps getting weirder. That's the name of it. So some people just coded it for fun. Some people, they do fun stuff. So first of all, if I'm in the middle, I don't know what's going on. It is very beautiful though. And I keep zooming in. This program is amazing. But when I zoom out, I see a big picture. That's what it's doing. Look at that. This is color coding by angles. I want to see the speeds. The speeds are also different. But angle was much better. This one. Isn't cool? And you can create your own if you actually want to. Okay, now it's actually broken. Something like that. And you can see much more there. There are more other cool stuff. I watch them all because it's really good. Let's do angles. Yeah, classical whirlpools. But I wonder if it's only one. So I'm zooming out. And yeah, it's only one for some reason. Is it interesting? So I highly recommend you to go and play with that. And I'm going to move on to the next chapter right now.